Hello, in this video I'll show you my paper that I published in the third International Conference on Computing, Mathematics and Engineering Technology. This conference is held in Pakistan on January 2020. The title of this presentation is Three-Phase D-STATCOM with Digital Current Control Strategy in ABC Reference Frame. Here is my name, and and this research belongs to a joint research which I have with some colleagues in South Korea and Pakistan. Introduction. Reactive power circulation in electrical system is under concern since Steinitz first identified such power on his apparatus in the 19th century, and so far the circulation of reactive power in the electrical system is kind complicated because you may draw back your system, you may deteriorate your power factor, so reactive power circulating in the system is actually unnecessary. And a lot of solutions were developed along the last decades in order to compensate reactive power produced or consumed by loads. One of the most common solutions is the STATCOM, which is a solution based on an IGBT converter. And STATCOM means the three-phase distributed static compensator. And the STATCOM, which is a quite familiar solution, is able to compensate reactive power at the point of where it is connected. And regarding the control strategy of STATCOM, the most conventional and the most preferable is the D-key rotating reference frame. So you make all your control strategy within this frame, D-key rotate reference frame. But this has a drawback because when you are employing a control in a DQ rotating reference frame, you need to have the PLL, and the PLL plays an important role in this system. So using DQ rotate reference frame is completely attached to the efficacy of the phase lock loop, the PLL. So if the PLL is deteriorated, all your system may be deteriorated as well. So the dependence of the PLL is strongly necessary, and this is a drawback of solutions employing DQ rotating reference frame. If the grid is distorted, for instance, the PLL may not track correctly the phase, so the transformation may not be good anymore. And the proposal of this paper is to present a three-phase D-STATCOM with digital current controller and its strategy all in ABC reference frame. This makes of no use of PLL, so we are not using PLL anymore, and the reactive power is transferred to the grid through controlling the D-STATCOM output current. And the current controller has 1, 0 and 2 poles, and this type of controller is also known as type 2 controller. This is also a different approach of the conventional STATCOM. On the conventional STATCOM we have DQ rotation reference frame and PI controllers, which is really easy and well defined how to tune it. And here in this proposal we are not using DQ anymore, we are using ABC reference frame. So the controller needs to be more sophisticated. In this case we are using a controller which has 1, 0 and 2 poles. The procedure to tune such a controller is explained in the paper, and also this is also a differential of our paper, that we are using the conservative power theory instead of the conventional PQ theory to compute the reactive power of the loads. And the theory, this theory here, the conservative power theory, is being broadly used in power electronics applications, especially those involving smart grids. It's a new theory, and it computes reactive power, active power, and harmonics currents in a good and satisfactory manner. Here is the system understood. We have here the three-phase electrical system. There is a line impedance, and this rectangle here is the point of common coupling, where we have a lot of loads. We have linear loads, these both are linear loads, and we have also non-linear loads. We have switches here in order to show that the performance of the STATCOM when loads are connected and disconnected. Even this for also for the nonlinear load, which is a three-phase direct fire. And here is actually our proposal. It's the STATCOM, the three-phase, it's here, which is a capacitor in the DC link. This is measured and controlled with this voltage controller. And I also have here a switch in order to connect and disconnect the STATCOM to the PCC. Here are the variables that we need to measure in order to compute the reference and also in order to use in the controller. Okay, so you have here the load currents. All the load currents are passing through this path, which are being measured and sent to our proposal. And also the voltage, the phase voltage of the PCC are sent to this block diagram. And this is where we have the control strategy of our proposal. First, load current and voltage current passes through this block, which is the conservative power theory, which in turn computes the reference for the current of the STATCOM. These are compared with the actual current of the output, and then we have here the current controller. Notice that there's no PLL. We have one controller for each phase, which is running in ABC reference frame. And again, this controller must be more sophisticated. We have also here the voltage control of the DC link. And we also have here a feed-forward path considering the voltage of the PCC in order to make it easier to control the output current. After computing everything, the PWM is generated, and also we have here the signal sending to the switches of the D-STATCOM. And this is our proposal, is to use ABC reference frame, avoid using PLL, so we have no dependence anymore of the efficacy of the PLL, and we see that these controllers are properly designed and is able to make this current to follow its reference. And the reference is also a differential of this paper, that is the computation of the conservative power theory instead of the conventional PQ theory. Designing the current controller. So we have here some equations in order to design those controllers. And we can take a look at the paper for more details of these equations. I won't take much time here on these equations. So we have here the rest of the equations. We need to point out that the controller is this one, is a digital controller. So we have here coefficients of the digital controller. We can here see how to compute all the coefficients of the current controller. So for more details, again, take a look at the paper. You can understand from where these equations come from. And also here, the CPT, the reference for the STATCOM for phase ABC are computed again with using this equation here. We have here an integral is called biased integrator. So we have here the definition. Again, more definitions of the conservative power theory references may be found on the paper. Results and discussion. Here you have a table showing the parameters of the case study and also already the coefficients computed according to the proposed procedure of tuning such a controller. The first results are two board diagrams. On the left here we find that the comparison between the analog and the digital controller. So in order to design the digital controller, we first design an analog controller and then discretize it. So you can see here the comparison between the two controllers. Actually, we are using the blue one, but at least we can see here that it is coincident for a long range of frequencies, which is enough for us to make the D-STATCOM working according to its expected. For magnitude and phase, the controller here, we can see that they are coincident for a long range of frequencies, which is enough. And here we have here the board diagram of the closed loop transfer function considering the controller. We can see here, even though there is a minimal disturbance here, we can see that there is actually a large bandwidth of this controller, which is able to make the D-STATCOM operate at 60 Hz, which is its nominal frequency. We have some results. Here we have the voltage at the PCC and the grid current. So we initially have just the linear load, and at this moment here is the moment where the converter begins to operate. So we see here that the inverter was out of phase. If you consider here the blue line, they were out of phase, and later they will become in phase because the reactive power is being compensated. Here again, we have here the current, the three-phase load current is linear, and here we have the D-STATCOM current at the same scenario, initialization. So we have here some spikes, but later after some cycles, steady state is reached, and we see that the compensation of the reactive power is being obtained. Here I have a result where is the reference. So we have here the reference. The reference is already computed by the conservative power theory, and in blue is the D-STATCOM output current. As soon as it begins to work, we see that the output current follows its signal reference without error, or with a negligible error. Okay, so we can see that the controller is well designed because the output current of the D-STATCOM, which is the controller variable, is following its reference signal with negligible steady state error. Here another results. This is the reactive energy along 2 seconds, and you have here the connections of linear loads and nonlinear loads. And we see here initially at the moment that the inverter is not working, there is a reactive power circulating through the grid. There are 3 signals here for phase A, B, and C. As soon as the inverter begins to operate, it makes the reactive power to go to 0. Here is the moment where a new load is connected, the linear load, and here we see is where the nonlinear load is connected. After the 2 connections of these loads, the D-STATCOM computes a new reference according to the CPT, the conservative power theory, and the compensation is being obtained as well. So we can see here that the efficacy of our proposal is verified because we are making the reactive power going to 0 for all range of time, and with connections and disconnections of loads, linear and nonlinear loads. And we can see here the DC link voltage in kilovolts, and we see that one is controlled as for a long time. So we can also have in here that the voltage controller is also well verified. And just one comment here, and here is written reactive energy because the conservative power theory defines the reactive power as reactive energy, but the concept they are quite similar. Okay, so reactive energy means reactive power in a broad concept of electrical systems. We can see here again that the reactive power is being compensated even in the presence of new loads and nonlinear loads. We may find more results of this proposal in the paper. I didn't place here all the results in order to save time, but you can go there and see other waveforms of the nonlinear loads and other scenarios. Conclusion, and this paper proposed a 3-phase D-STATCOM with digital current controller, and its strategy is running in ABC reference frame. This was the proposal, not to use a PLL and to use the reactive power, the conservative power theory to compute the reactive energy. So we are avoiding using matrix transformations which are dependent on the PLL. This is the most proposal of this paper, and also showing how to tune a digital controller for such application. The procedure to tune the controller was explained. A case study was conducted through simulation, and this showed the efficacy of the proposed D-STATCOM. The measured variables did not present neither unpredictable nor oscillatory behaviors, and we saw also that the steady state errors were negligible, and therefore the proposed D-STATCOM controlled in ABC reference frame is an attractive solution for reactive power compensation in 3-phase systems. And just one acknowledgement, I'd like to thank to the CNPq for sponsoring this research. And also, I'd like to say before wrapping up this presentation that the simulation files I used in this paper are freely available on my webpage. You can just go there and download the files that I used in this paper. They are ready for Simulink running. Thank you so much. If you have some questions, you can send me an email. I'll be so glad to answer. And thank you for watching this presentation.